All right, guys, we're going to go back and talk a little bit about Chapter 10 because it could be on the AP exam. It is one of the chapters that's possible. So I feel like it's important that we go back and do it. So Chapter 10 deals with what if your scatter plot is not straight? And how can we make it straight so that we can make a linear equation? And it's more of like a guess and check process, so it's not as daunting as it seems sometimes. So why would we re-express? Well, one is to improve the symmetry of the graph. Another is to make several groups have a more near equal spread. We could make the form of a scatter plot more linear, and we can make a scatter plot have a more consistent spread throughout. So those are some of the reasons why we want to re-express data. Now, when we're re-expressing data, we start with the raw data. The raw data here is 1. Okay, anything to the 1 power is itself, so that's where your raw data lies. And we normally go down this ladder of powers to determine how we can make the data straight. So we start actually with 0, the logarithm. And we start by taking the log of the y values against x and see if that is straight. If that doesn't, then we look at the log x and the y, and then we look at log x, log y. This is where we start, okay? This is where we find the most effectiveness. And if the data has zeros, though, we have to make sure that we add 1 or write the numbers slightly differently so that we don't have a domain error, because if you remember, we can't take the logarithm of 0. Then you could possibly use the square root of y. If that doesn't work, sometimes we try the reciprocal. The reason we see -1, the negative reciprocal, is it keeps the graph in the same direction. If we do the reciprocal of a graph that's positive, it's going to end up being negative. So we do the negative reciprocal, and that makes it positive. We do the negative reciprocal of the square root. That could possibly work. And sometimes, rarely, the square of the data will actually make the data straight. When the data is unimodal and skewed to the left, sometimes squaring the values will work. This is not, the reciprocal square root is not a very common one. So we'll look at, sometimes we can also look at the ratio of the two quantities, and if we know it has this kind of like reciprocal relationship, that might be a good one to try. So here we have the population data for the United States from the year 1800 in 25-year increments all the way to 2000. We're going to scale the years. But if we use 0 when we do the log expression, it's not going to work. So when we put it in our data, we're actually going to call the year 1800 year 1. So we're going to call this year 1. And so it's going to be since 1799. And then we'll call 1825 26 and 51 and 76 and 101. The reason we do this is it keeps our numbers a little bit smaller, because putting in 1800 and all that makes our numbers larger. So 126, 151, 176, and 201. Those will be our new x values, and the population data we'll put in. Now I'm going to shrink this down because I'm going to have to show you the calculator. So go ahead and take a second, pause the video, and put this stuff into your list 1 and list 2. Clear everything else out because you're going to need all your lists. Okay, so we have the data in our calculator. So we're going to look at the scatter plot. So second, stat plot. We haven't done this in quite some time, so remember you just hit enter. And then we're going to turn that plot on. And we're going to go to the first one, which is your scatter plot. And my list 1 is my X list. My list 2 is my Y list. Okay, and so we're going to hit zoom 9, which is zoom stat. And we can clearly see that the data is, let's see, remember how we described distribution, or like scatter plots. Direction, positive. Form, curved, right? Scatter, tightly scattered. I could draw a pretty good line through all of those points, right? And then there's no apparent outliers. So direction, form, scatter, outliers, that's what we're looking for. Now, I want to look at the residual plot, but remember, to look at the residual plot, I have to go into my stat calc 8. I have to do my lin reg first. in order to look at my stat plot. So list 1 and list 2. And I can store my equation, remember? Vars, y vars. Gosh, I almost forget. Enter, enter, and that puts my equation in the y equals menu. And hit calculate. So this is my correlation, right? My correlation in my r squared. My correlation is 0.956, which is pretty good, but we can clearly see that there's a curve in the graph. Look at the scatter plot. The linear model actually fits it pretty well according to our correlation and our r squared, but it's not straight when we can see that. So we want to look at the residual plot. So we go to stat plot. Oh, second stat plot. Turn this on, and I'm going to go to my y list, and now I'm going to put in resid. So we go second list, and I like to go up because it's normally at the bottom, and then zoom 9 again. And remember what we were looking for in a scatter or residual plot is that it has no direction, no form, right? And it's randomly scattered. This is clearly has a direction and a form, which means there's a pattern in the data that our equation and our line or model is not fitting. Remember that the model is the equation of the line. So it's clearly there's a pattern in my scatter plot, so a linear model is not appropriate. Remember, that's what that means. So the question is, what do we do next? So let's go into our data. And luckily our calculators do all this lovely work for us. I'm going to take the log of list 2, which is the log of y. Okay, so and it might be good to write down that list 3 is the log of y. Okay, and then I'm going to go into my stat plot, and I'm going to turn my y list to list 3. And we're going to zoom 9 and see what happened. Well, there's still a curve and it's the opposite direction. So clearly that didn't make it straight. This line is my y equals, right? My last regression line, I can clear that out if I don't like it. So I'm not going to bother doing a residual plot because it's clear that that's also curved in the other direction. My residual plot will show a curve as well. So I'm going to go stat edit, and in list 4, I'm going to do the log. So I hit just log. Remember, we were highlighting list 4 up here, the log of list 1, which is x. And I'm going to write off to the side that list 4 is log of x. That way I keep track of what I did in each one. And see, it's really important that we have this number as a 1, because the minute I would try to do that into this list, if it was 0, I would get undefined, and then it can't graph it for me. And so then let's look at the stat plot of list 4, stat plot, list 4 and list 2. So this is the graph, list 4 and list 2 is the graph of the log of x comma y, and then we did x log y just before that. And then next we'll do log x log y. And so I'm going to zoom 9. Ooh, that made it even more crazy curved. So that didn't straighten it. And so go into my stat plot again. And now we're going to look at list 4 and list 3. That's the log x. The log of x is my list 4, and the log of y is my list 3. We'll zoom 9, and that also did not straighten the data. So none of these worked to make it straight. Okay, this is clearly curved. You can see that curve here like that. Okay, so now we've gone through our log. So the next thing is to try the square root re-expression. So, and I leave it in my calculator because sometimes we see a little curve and then we go through all of the process and we don't find one that we think works, so we have to go back and look again. So I just keep this list of what I've done in my calculator. So list 5, I'm going to do the square root of x. I'm sorry, not square root of x. We want to do the square root of y. So I'm going to do the square root of y in list 5. So I'm going to highlight list 5, and I'm going to do my, stat edit, highlight list 5, square root of list 2, that's my raw data, and then we're going to zoom 9 and see what happened. Well, that didn't work either. Wait, I didn't change my stat plot. Oops. Go back to my stat plot and change that to list 1. List 1, and then list 5. So make sure you change your stat plot before you look at your graphs. Ooh, that looks pretty straight, doesn't it? Look at that. That looks pretty straight. So let's see what we get when we create a linear model. So I had a little number in here. Let's take that out. And we're going to go stat calc 8. It's list 1 and list 5. We can store our regression equation, vars, y vars, enter, enter, and then calculate. Now look at our R. Our R went from about a 95.8 with the with the first linear model, and now it's 99.6 or 0.996, and our R squared is 99.3. So that looks really good. So I'm going to write down my data here because my R is really good. Remember that A is your y-intercept and B is your slope. And R squared is 0.993, and R is 0.996. So now let's look at a residual plot. Stat plot, and sometimes it's nice to go in and use a different menu or a different stat plot just for resid, and you always have resid and y-list, and you just keep changing your x-list. But I'll just use this one, zoom 9. So here we have some pretty random scatter. Doesn't seem to me, there's a little pattern, but it's looking pretty good. Let's look at our size of our residuals. So let's hit trace. When we look at our largest residual here, it's 0.76. That means the actual value is only 0.76 higher than what the line predicted. And as we trace through here, we see that's negative 0.01, negative 0.39. So these are all really small residuals, which means if we go back and look at our scatter plot, that the line practically fits it perfectly. So we found a good model. So how do we write the equation of that model? So our equation is the square root of y, the square root of the population hat, right? Remember we put the hat because it's the predicted value, is equal to our y-intercept. That's, we use b naught in our book. It's a in the calculator, 1.394 plus 0.0744 times years since 1799. It's important that we put that in there because we're not going to actually put in 1800. We're going to put in 1. We're going to put in 26. And if we went back and changed it back to 0, that would be okay because we're not taking the square root. There's no undefined values. But since we did that for the logs, we're just going to keep it. And so this would be our equation. And now, the next thing is, what if we wanted to make an estimate of the population in the year 1940. So can we use this model? Well, yeah, 1940 is in the scope of our data. It's within what we have here, so we can use that, but 1940 we would put in as 1940 would be 141 years since 1979. So we'd put that in. The square root of the population hat equals 1.394 plus 0.0744 times 141. And we'll do that in the calculator, and I'm going to spare you watching me plug that in. So 1.394 plus 0.0744 times 141. And I get the square root of the population hat equals 11.88. Now I haven't actually found the y value of the population yet, so I need to square both sides and square that number. And we get the population, predicted population for 1940 is 141.24 million. Now, could we use this model to predict what it's going to be in 2025? No. Okay, our data stops at 2000. If we had 2020 data, right, this book, remember, our book's a little old. We don't have the 2020 census data yet. If we had that, then yes, we could probably make a better prediction. But right now, 25 years is too far out of the scope of our data. And remember, that's called extrapolation. So extrapolation is when we try to make a prediction too far outside of the scope of our data. So we wouldn't want to do that. All right, and that's basically the process of re-expressing data. It's a big guess and check model. First, check. So step 1 is to check x log y. Step 2 is to check log x y. Step 3 is to check log x log y. Step 4 is x square root y. Step 5 is x 1 over y. Step 6 is x. We could do negative. It preserves that negative 1 over y squared. And 7 is x and y squared. Notice that it's only in the logs that we change the x's. And the other ones we're only changing y. And we just go through, we look at our scatter plot. We look at residual plot. If there's a pattern, but the scatter plot fit it really well, look for really small residuals, because the calculator zooms in really close on those residuals. So even if there could be like 0.000001, it's going to make it look like there's a pattern. So you might want to zoom out sometimes on the residual plot if your numbers are really big and it looks like it fits well. Okay, so let's look at some more things. Suppose the correlation between SAT verbal scores and SAT math scores is 0.48. So R is 0.48. And that these scores are normally distributed. If a student's verbal score places her in the 80th percentile, what percentile would you predict her math score to be in? So we can use the fact that it's normally distributed to find what the actual z-scores are. Because remember, we said if a correlation is 1 standard deviation on the x, we expect 1 standard deviation on the y. If r was 0.5, for 1 standard deviation on the x, we expect 0.5 standard deviations on the y, and so on. So if r is 0.75, 1 standard deviation on the x, we expect 0.75 standard deviations on the y. So we need to know how many standard deviations from the mean this 80th percentile is. And to do that, we can use inverse norm, because we want the 80th percentile, that's the lower 80%. So we're going to inverse norm 0.8. And when I do that, it's in second distribution. Number 3 is inverse norm 0.8. I'm going to leave it at left. And I get 0.842. So I'm 0.842 standard deviations from the mean on the x. That's the SAT verbal score. So we're going to multiply that by 0.48 because that's how many standard deviations we expect on the y. So that times 0.48. I'm not rounding in my calculator. So we get 0.404 on the y. And then I'm going to use Normalcdf to find what that percentile is. So Normalcdf. And percentiles is less than, right? So if I'm at 404, I want the percentage below it. So I'm going to do negative 99, comma 0.404. So second distribution, Normalcdf, negative 99. I'm going to use second answer. I like it to be not rounded until the very, very end, and that's 0.657. So we expect the SAT math to be in the 66th percentile if the SAT verbal was in the 80th. So the calculator has some shortcuts in where it fits a curved model, but we really don't want to be using those much. The natural log regression is when you have, so you have ln reg, exponential reg, and power reg in the calculator. And so the re-expression that would fit that would be the log of y for the exponential regression. But then what it does is it writes it as an exponential model, like a times b to the x power. And then the logarithmic one, natural log, writes it as the log of, a times the log b. And then power is like x to a power. But really the expression, the re-expression, is more important for our unit. So we're not really going to use the calculator shortcuts. Okay, so here's a little bit of algebra review. If we are looking to find y, the predicted y, when x equals 2, it's important that we remember how to solve log equations. So for a, it's y hat equals 1.2 plus 0.8 times the log of 2. And y hat equals 1.2 plus 0.8. Plug in the log 2 in your calculator, we get 0.301. And then if when we multiply that, we get 1.2 plus 0.24, sorry. 0.241. And then we add that together and we get 1.441. So y hat equals 1.441. B is a little bit harder. B is the log of y hat equals 1.2 plus 0.8x. So 0.8 times 2. How do we solve that log equation? 1.2 plus 1.6. Log of y hat equals 2.8. So we mainly solved these equations by rewriting it as an exponent. So to rewrite that as an exponent, remember that log of x is log base 10. So the inverse is 10 to the x, right? So it's 10 y hat equals 10 to the 2.8 power. And when I plug that in my calculator, we get 630.96. C is the natural log. Remember, the natural log is log base e. So ln of y hat equals 1.2 plus 0.8 times ln of 2. So the natural log of y equals 1.2 plus 0.8 times the natural log of 2. We'll just plug that in the calculator. 0.8 times ln of 2 is 0.555. Add 1.2, so the natural log of y hat equals 1.755. Now to rewrite that as an exponent, it's y hat equals e to the 1.755. And the e button is above the ln, so e to the 1.755 is y hat equals 5.78. And then D and E are a little less complicated. Well, maybe not E, but we'll move some of these out of the way. And we'll get y hat squared equals 1.2 plus 0.8 times 2. That's y hat squared equals 2. We just did this. That's 1.6, so 2.8. And then we'll have to take the square root of both sides. Y hat equals the square root of 2.8 is 1.67. And then E, that's D. E is 1 over the square root of y hat, which is 1.2 plus 0.8 times 2. Again, that's 1 over square root of y equals y hat equals the 2.8. So we're going to multiply by square root y. So 1 equals 2.8 times the square root of y hat. And then we're going to divide by 2.8. So 1 divided by 2.8 is 0.357 equals the square root of y hat. And to get rid of the square root, we're going to square both sides. And so 3.57 squared is 0.128. So y hat is 0.128. Okay, we're going to look at one problem together, number 14 out of the chapter 10 problems, height and pressure. So pause the video real quick, take some time to put this into list 1 and list 2. Okay, we should have that data in list 1 and list 2. So remember, list 1 is going to be our x values, list 2 is going to be our y. Then in list 3, we're going to do the log of y. List 4, we're going to do the log of x. List 5, we're going to do the log, the square root of x. And then if we have to in list 6, we'll do 1 over x. And we'll go from there. All right, so here's my calculator. I have my data in list 1 and list 2. We're going to look at the initial scatter plot. I have a plot 1 on, plot 1 and 2, list 1 and list 2. So I'm going to zoom 9. And we can see it's not straight, right? So we want to look at the residual plot. We want to do that first for our data, but we can see this is a downward curve. So let's go into how do we get the residual plot? We have to do the linear regression first. So linreg 8, list 1 and list 2. Store my equation, vars, y vars, enter, enter, and then hit calculate. So there's my regression, and you can see my correlation is actually pretty good. So let's look at the graph again. The correlation is pretty high, even though it's clearly not straight. So the linear model is not appropriate, and that's why it's really important to look at the residual plot, because the correlation in itself doesn't tell us all the whole story. So I'm going to come here and turn this to resid. So I go second list, and I always go up because it's at the bottom, and I'm going to zoom 9 again. And you can see in the residual plot there's a clear curve. There's a clear curve here, and so a linear model is not appropriate, and we could tell that from the scatter plot. So we'll go into our lists, stat, edit, and sometimes it's really easy to just go log of list 2, that's the log of y. We said that was going to be that list. Here I'm going to go log of list x, or list 1, the x list, and then here I'm going to do the square root of x. Oops, that's list 1. No, sorry, I want to do list 2, square root of y. And now I just have those lists set up for me, so I can just kind of go through my scatter plots really quickly and see which ones look straight. So if it looks straight, then we'll look at the residual plot. So I'm going to look at list 1, list 3. That is the x log y. So zoom 9. And we're going to have the old line in there. And that looks better. So let's do our linear regression. Calc 8, list 1, list 3, and calculate. We see my correlation is up. It's 0.985. It's negative because it's a negative line. The slope is negative. Let's look at that graph. We can see it fits it pretty well, but it kind of looks like there's still a pattern. So let's look at the residual plot. Now that I've done the linreg, my residuals are for this particular two lists, which is the x log y, and zoom 9. And again, we see the same basic pattern in our residual plot. Sorry, I didn't realize that was not in the camera the whole time. So now let's go back and look at list 4, that's log x, and list 2, that's y. And we can see that from here, right? And then zoom 9. Still looks curved, so I'm just going to skip doing the residual plot on that one. It looks curved still. Let's do x and log x and log y. So zoom 9. And that actually looks really straight. So right now we are at log x versus log, I don't know what that was, y. That looks really straight, so I'm going to go stat calc 8. List 4 and list 3, put my equation in, oops, vars, y vars, enter, enter, and look, it's a negative 0.9999. Let's look at the graph, and it's almost going through all of the points. So it looks really good. Let's look at that residual plot, second stat plot. We're going to do the log x's versus the residuals. So second list, resid, zoom 9. We can see it's pretty scattered. There's no apparent pattern or increasing spread. And let's trace them just to see how small they are. Look at how small those numbers are. Those means the residuals are really, really close. So sometimes it's good to zoom out just a tad, and it kind of gives us a better picture of what's going on. I kind of prefer to look at the windows. Let's go from a minimum of -1 to +1. That's a reasonable residual plot, and we can see they're all on the line. My X values are a little off because I did the zoom, but that kind of, zoom 9 again. Let me zoom 9 again, and then we'll look at that window one more time. We're going to go from, how about just negative 0.5 to 0.5. And you can see they're like all right on the line because they're almost 0. That means it's a really good model. Okay, so now we got to go back and look at our linreg. So I went back, I did the linreg again on list 3 and list 4, and I get that A is 3.15 and B is negative 1.001. My R squared is 0.999 and R is negative 0.999. And so my equation is going to be the log of, what are we talking about, pressure hat equals 3.15 minus 1.001. Let me erase that little bit there. I don't have enough room here. 1.001 log of height, because I did the log of x and the log of y, and that is my re-expressed equation with an R of negative 0.999 and an R squared of 0.999. So it's also really good to practice interpreting your R squared as we do this.